In the previous lecture, you were introduced to scaling effects and broad notions on how to minimize them. As you learned, this is not straightforward, as not all aspects of a process scale to the same degree. It was therefore suggested to focus instead on similarity. But what does similarity mean? In this lecture, we will dive somewhat deeper into this concept. Let's consider scaling a certain process from a beaker by a factor of 1 million to 100 to 500 cubic meters, the size of an industrial reactor. In principle, we could design these reactor geometries to be the same, a big cylinder filled with liquid with a certain aspect ratio. Now consider that we are heating this reactor by putting it on a hot plate, and we want the contents to heat up and boil homogeneously. In the small beaker, this is not an issue. The heat distributes sufficiently rapidly through conduction and natural convection. In the large reactor, however, we may find that water in the bottom may boil, while in the top it's still relatively cold. I may need to pump or to mix actively to ensure that heat is distributed sufficiently rapidly. In addition, scaling up leads to a different area to volume ratio, which reduces the rate of heating, which requires additional heat transfer surfaces to remedy. Overall, to achieve similar behavior between these two systems, we need to use different equipment. Now, if we want to scale up or scale down our process, we are looking for similarity in behavior, which requires a different approach than just changing the size of our equipment. And it's essential to know which physical phenomena control the process and to make sure that the impact of this remains similar or the same between scales, while we can apply some more leeway in scaling the physical phenomena that have a negligible effect on the process. There are several ways to approach this question. We can both address what to keep similar and how to keep these things similar. And approaches range from quick and crude to get a general feeling of the most important physical phenomena to very detailed, suitable for example to decide on which impeller type you're using or which heat exchanger configuration or which microbial strain is the most suitable for your process. The simplest approach are to apply known rules of thumb for scale-up. Experience may dictate which factors are important and which scaling approaches do and do not work. Now, this approach is very common and it can be powerful, but it may also be dangerous. Focusing on one rule of thumb may lead to oversight of other relevant aspects, with all due consequences. So they may be useful, but they should always be part of a broader, structured approach. As such rules are often case-specific too, we will not further address them here. Slightly more detailed is the use of dimensionless numbers, such as the Reynolds number, the Nusselt number, and the power number. And what these numbers signify is the ratio between the contribution of two physical processes. In case of the Reynolds number, this is between viscous and inertial forces. More generally, it can be the ratio between forces, between length scales, or between time scales. Now, the archetype example of the Reynolds number lies not in chemical engineering, but in aerodynamics for the design of wind tunnels. It may look like wind tunnels are just simple cases of geometric scaling. Here we just show a miniature car, right? But there's more to it. Important design parameters like the drag and the lift coefficient depend on the Reynolds number. So if we want to judge aerodynamic behavior of a real car, we should strive for similar Reynolds numbers at small scale. And since the scale of the car is changed, one also needs to adjust the velocity or the fluid properties to achieve the same Reynolds number. We will dive deeper into the use of dimensionless numbers in the next module. But do we need to match the values of these dimensionless numbers exactly between the scales? Well, not always. As you may remember, at certain Reynolds number, the flow in a pipe transitions, for example, from laminar to turbulent, and some parameters, such as the drag force on a spherical particle, become constant once you reach the turbulent regime. And in these cases, it's not needed to exactly match the value of the dimensionless numbers. For similarity, it suffices just to be in the right regime. Well, of course, this requires to know where the threshold between regimes lie. Transitioning to another regime means a transition in the dominant transport mechanism, which is to be avoided when we're conducting scaling exercises. Dimensionless numbers can hence tell you which scaling parameters should be matched exactly, which should at least be maintained in the same regime, and which physical phenomena are non-influential and can be ignored upon scaling, at least to a degree where we do not observe a regime change which would change their relevance. Related to timescales are balances. Coarsely speaking, at whatever scale you're operating, what goes into your system has to come out in one form or another, but the dominant physical mechanisms by which this happens may be scale dependent. By setting up balances and making them dimensionless, you gain deeper insights regarding which physical effects play a role and what their approximate quantitative influence at different scales is. This will be further treated in one of the next lectures. A particularly useful aspect of balances is that they provide insight in the timescales of the involved processes, which is very powerful. The timescales of processes show which mechanisms are dominant and which ones can be neglected, and changes in timescales can indicate changes in regimes. In addition, solving the balances can provide insight in quantitative effects of scaling. But for now, let's avoid such details and return to analyzing the timescales. For that, we revisit our beaker versus reactor example, but now including a chemical reaction. Unwanted byproducts may be formed if the contents of the reactor are not properly mixed. We noted before that mixing time varies hugely between the small beaker and the industrial reactor. For the small beaker to be well mixed, the mixing must be faster than the reaction time. So we need to look at the ratio between the mixing time on one hand and the reaction time on the other. Now, if the reaction runs very slow, for example, it takes 3 hours, mixing will not be an issue at either scale. But what if the reaction time is only a minute? In that case, behavior will be notably different between the small and the large beaker. We've transitioned a regime from well mixed on small scale to incomplete mixing in the reactor. Using timescales, dimensionless numbers, and balances, we can use them to identify if scaling issues may arise. A further question may be, what kind of impact do these scaling issues have? With some simplifications and added physical models, balances may already provide us with estimations. For example, you may be able to estimate the concentration difference in a certain reactant between the top and the bottom of a beaker, and the effect that this will have on byproduct formation. But for complex reactor configurations, such calculations become very elaborate, and far more detailed insight is needed, for which you may resort to fundamental methods such as computational fluid dynamics. These methods consider the same balances, but in much higher resolution, providing detailed insights in possible local scaling effect. Such methods may be used, for example, to evaluate how different impeller configurations in the industrial reactor affect mixing time and hence how prominent scaling issues may be. Fundamental methods are very powerful and can provide great insights, but they're also laborious. You typically use them if scaling issues are unavoidable and you need to know their impact. To recap, scaling relies on similarity. When moving between scales, some parameters need to be matched exactly, while for others you just need to be in the right regime. And dimensional analysis and balances with their respective timescales provide insight in what to keep similar. Finally, physical models based on balances can help provide insights in the impact of scaling effects. In the coming videos, we will explore these techniques in more detail.